That was before it started. So, hey, hello, welcome. All right, so before we even get started, I want to do a little bit of intuition because the comparison tests are a little bit even weirder than some of the tests we've been doing in that you're very much going to know the answer to your question before you get started. So for most of these, we are going to know converge, diverge from like the very first step we do. And then these ones, it's very much about creating the argument of why does it converge or diverge. Now, looking at these series, do you guys agree with me that they all kind of look like something we've done so far with, well, maybe not the last one, but with a little bit of a change to them? So like this first one, does it look like a type of series that we did before? What does it kind of look like? All right, it looks like some of the integral test ones we did, even simpler. I think it looks like a P series. Anyone else think it looks like a P series? Like if I just looked at that part instead of the +1, let me rewrite it. Maybe you'll see. So if I wrote it like this, now I can't just take that +1 off, but do you agree that those look kind of similar? All right. Now, if I push n to infinity, how much of a difference do you think that +1 on the bottom is going to make? Very, very small. So this is a P series. Let's review. What's P equal? Why do I care? So it does what? Let's go with converges. Bigger powers make the bottom smaller. That's helpful. All right. So we're going to have to find a way today to construct an argument. But our first step is going to be choosing this thing. Hi, Miss Riley. Me? What a lucky lady. All right. As I scroll down, I want you to think about what would you compare this one All right. Anyone have an idea of what I could compare this to? Think simpler. Think simpler. What does it look kind of like? Oh, wait. All right. What kind of P series? Does it look kind of like the harmonic series? Yeah. All right. If I just drop that -6, because how much is that -6 really doing? We're going from 7 all the way up to infinity. That's a lot. That's a lot of terms. All right. Why do you guys think this one starts at 7, by the way?
Because 7 minus 6.
Yeah. Wouldn't 6 cause issues? Yeah. So here. All right. So what was this guy's name?
Harmonic.
Harmonic, which is a special type of P series where P equals 1. What did he do? He diverged. All right. Okay. So we took off the 1. We took off the -6. All right. What do you think this one looks kind of like? Ooh, it does look kind of like a geometric. Let's say I get rid of that stuff. What power or what would our ratio be to the nth power? All right, 2 on the bottom. I can add a 1 on the top because 1 to any power is whatever. All right, so this is geometric. We were just talking about R. What is R? Sorry, R is 1/2. Absolute value is 1/2. Why do I care?
Less than 1.
Converge or diverge? Converge. We're going to get a lot of practice with these today with the P series and geometric. Usually we're going to compare to those. So remember, for geometric, we want to multiply by a fraction every time. We want to make our number smaller. So that's why we like numbers that are less than 1. So that's kind of what we're going to deal with today. And we're going to learn today is how do I construct a very formal comparison. So let's just continue. I have 2 more where I want to get some intuition about how to find the series we're comparing to, and then we're going to get to the formal argument. All right, what do you think I'm going to do here? Yeah, do you guys like the idea of maybe a geometric again? What would you drop? All right, I dropped the -n because do you agree with me? 3 to the n grows way faster than n does. Exponentials grow really fast, right? So let's review. We've got, could I pull this n out, make a fraction inside? Yeah. All right. So you guys said this is geometric. What do I look at for geometric? All right. Absolute value of R. So this case is 4/3. Why do I care? So this does what? Yeah, so since that one has the N on it, one of the ones you did in your notes check, this guy didn't have an N on it, so he would have to stay out here. If he does, I can bring him inside. All right, now, when we finish today, we're going to get to some more complicated series like this. I want you, while I pass out the notes, I want you to take a second and see how simple a series you could compare this to. So what are you going to drop off? What are you going to keep? What's going to be a good series to compare this to? We'll talk about it. We'll definitely practice more with this today because we're going to get a formal way to compare these two guys. So while I pass these out, contemplate. I'm going to give you the notes. Yeah. I wouldn't make you do something.
There you go.
Oh, maybe that's you. Look a lot.
I know. And then something else, I don't know. Oh, yes.
We got no staple notes coming at me.
It looks like there's a lot there.
Paper cut. We have, yes.
Are we going to have a break?
Yes, we're going to do direct comparison and we'll break this before we do the
How long is that supposed to be?
depends on how brilliant you guys are. All right, anyone have an idea? What would you keep? What would you drop? What was your idea, Ashley?
I was going to say that you take like that and away from the 5 like,
Okay, so we can kind of just like disregard him. Is that what you're saying? Or something else?
that was the one that was like exactly saying.
Okay. What were you saying?
I was saying like you take like so like you have
Oh.
like you pull one out of the
I could factor out an N?
Yeah.
Is that what you're saying? I could do that, certainly. So if I factored out an N, that could certainly help me start to simplify. All right. Anyone think they know what they would keep out of this or out of this? Okay. So here I could cancel the N, certainly. But as we're trying to compare, how simple can I get this? What do we think doesn't really matter as far as this series goes? -5. Get rid of it. Probably not super helpful. All right. What else do you think doesn't really matter as far as like convergence, divergence goes? The 6 probably doesn't matter that much. So if I'm comparing, wow. All right. As we're comparing, I'm really looking at n over n to the 4th. What does that simplify into? 1 over n cubed. Is that a type of series we know? Yeah, what type of series is that?
P-series.
It's a P series. P equals 3, which is greater than 1. So this does what?
It's on the bottom. It's on the bottom.
Okay. Yeah. So for powers, you want bigger powers on the bottom. So P's that are big are good. Ratios, you want to multiply by small numbers to make our numbers smaller. So small numbers are good. Notice here, we could look at n squared over n to the 5th, or in the one that Ashley had, we could look at these powers here, kind of divide those. So we're looking at kind of greatest powers top and bottom. Now those could be powers, so like a P series, or we could be looking at exponentials like these. Most of the things we're going to compare to are going to be either geometric or P series. The reason for that is we're going to have to tell what that thing we're comparing to does. So one of the reasons people don't like comparison tests that much, even though they're super useful, is it's going to kind of feel like we're doing 2 convergence divergence tests. One for the one we're comparing it to, and then the actual comparison test. That being said, the one for the one we're comparing it to, usually we're going to use geometric or P series. So it's not going to be like an integral test and then a comparison test. So we're going to do 3 questions with direct comparison test. And then we're going to flip and do 2 questions with limit comparison test. I will tell you, I have a very strong preference for limit comparison test personally, because even though it's a little bit more work, it works for all of the problems. Direct comparison test only works for certain problems and not for other ones. So I'm going to like talk out the top of this. It might not make a lot of sense until we actually do a question. So give me at least until we're done with the first question before you yell at me that you don't understand. So we've got 2 series here. I'm going to be talking about A sub n and B sub n. Those are our 2 nth terms that we're talking about. I'm saying that they're both greater than or equal to 0. So that's essentially saying all of my terms are positive. So I know Ashley brought up alternating series earlier. We're not dealing with alternating yet. Or sorry, Jillian. Yes, who said alternating? Jillian, sorry. Spread it away from Ashley. Pass it to Jillian. So we are dealing with only positive terms. Now, we are going to compare the sizes of these two series. So let's say we know about a B sub n. So we know that B sub n, whatever that is, when I add all of those up, I get a convergent series. Let's also say that I know that A sub n, all of those terms are smaller than the ones in the series I know converges. What I can then claim, since I'm adding up a bunch of numbers that are definitely smaller than the ones I know add up to a number, A sub n has to converge as well. So one way to say this, if you're kind of saying it in words, which is how I think of it, is smaller than a convergent converges. Essentially, the idea is if you add up smaller numbers than ones you already know add up to just a number. They're not big enough to go to infinity. If I'm adding up smaller stuff, it should add to a smaller sum. So if I know things all add up to 4, I have a bunch of numbers that are less, they're going to add to a number less than 4. So I know if it's smaller than a convergent series, it has to converge. We can also go the other way. So let's say I know about the smaller one now. And I know that if I add up all of the terms of A sub n, I know I'm getting infinity. So we could be doing 1 plus 2 plus 3 plus 4 plus 5. That's going to infinity. It's too big. Well, what if the numbers were 1 plus 5 plus 10 plus 15? That's bigger. So I know it's going to have a bigger sum. So this one is going to diverge. So I was going to use the word bigger. You could use the word larger. Bigger than a divergent. Divergent. Exactly. So we're just getting a bigger form of infinity there. Now, you might be noticing that this inequality has to work a certain way for me to use this test. So I could be comparing to a divergent series, but have something that's smaller. In that case, well, all the numbers are smaller than infinity, so I have to use this kind of carefully. An inequality has to work. So let's do a couple of questions with this. It's going to feel a little weird at first because we have to use kind of our noggins to help us find a series and help us set up an inequality. So for the comparison test, the first thing we have to do is we have to pick what we're comparing to. Notationally, I want you to make sure when you say compare to, we need to compare to another series. So please don't drop your series notation. That's one of my biggest pet peeves is some people say like compare to and just write the nth term. We want to compare a series to a series. All right, we did this one already in our little intuition check. What do you think we are going to compare to in this question? 1 over n cubed. So we want to choose something that looks very, very similar, but kind of drops the extras. We're hoping to get this down to either a geometric series or a p series, ideally. Which one is this? What kind of series is this? All right, p series. So what's p? 3. Why do I care? So this does what? Good. Bigger powers are better. So 3 being bigger than 1. All right, so that's nothing new. Now what we have to do is we have to compare the thing we want to know about to the thing we do know about. So I have 1 over n cubed plus 1. This is the one I want to know about. This is the one I do know about. In this space right here, I'm about to write an inequality symbol. When I say that, I mean like mostly greater than or less than. I'm going to write the one that I want it to be, and then we're going to check to make sure it is. So if I have something that converges, what do I want this thing that I don't know about to be in relation to the thing that converges? I want it to be less than. Now, there's a couple of options here. If you look at this, is anyone convinced that that inequality symbol is correct? All right, I see a bunch of people nodding yes. I am also convinced. If I add 1 to the denominator on the left, that'll make the fraction smaller than the one on the right. If you are not convinced, I'm going to write some optional work in green. You can kind of cross multiply here and get n cubed is less than n cubed plus 1. Subtracting the n cubes, I get literally 0 is less than 1. So if you want to be a little more rigorous or you're not super sure, you're more than welcome to multiply things over and get a very firm statement saying that this converges. But if you can see it, I can probably see it too. So we are good with our comparison. Yes. Yes, we would want to be bigger than the divergent series. Exactly. So if that inequality is true, I can make my conclusion. I'm going to say that this converges by direct comparison test. Now, some of you are like, direct comparison test, that's a lot of writing. Good news, DCT. Acceptable both on my test and on the AP test. Ma'am.
Are we gonna have are we ever gonna use the greater than or less than equal to on them?
So you wouldn't really use equal to, because if it were equal to, you would probably just simplify and use the p-series test. So for example, if this had been 1 over n cubed, or if it were even n over n to the 4th, I would just simplify that and just use the p-series test. So for here, I'm usually just going to use greater than or less than. If you add the or equal to, you're not wrong. So. All right, let's try this a couple more times. So what shall we compare to? Okay, so you guys are taking a couple steps at once, which I love. I love that you're looking at the geometric. What I'm doing is I'm ditching the +2. So I've got 1 over 3 to the n, which is probably what you guys are saying is what to what the n power?
1/3.
1/3. All right, what is that 1/3 called if this is geometric? The ratio, which we call r. All right, remember we absolute value that and we get 1/3. I heard some stuff. Why do I care about the number 1/3? Less than 1. So what does this geometric series do? Converges. We want to be multiplying by smaller and smaller fractions. So good news there. So let's see if we can get this. I'm going to do the one I want to know about and the one I do know about. All right, the one I do know about converges. So what inequality symbol do I want to have there? Less than. Is that inequality symbol true? All right. I think it is because I'm adding 2 to the denominator. That should make my fraction smaller. Again, if you want to be convinced, here's some optional work you can do. You can multiply the 3 to the n to this side, the 2 plus 3 to the n to this side. Subtracting the 3 to the n's from both sides, I get 0 is less than 2. So if you want to be super rigorous, you're more than welcome to do the stuff in the green, or if you're just not convinced. You could also do direct comparison tests on more complicated series where that inequality is more helpful. But here we are. What am I missing? Perfect. Yeah.
We're gonna have to make pieces that it converges and you want it to be a less than sign, but it might.
Yes. So Nazi's already kind of looking ahead to what if this doesn't work. So we may get a case. Let's say I shoved a -2 on this. That's going to make this not true. So direct comparison doesn't always work. That's when you would move to the thing we're going to do after break, which is limit comparison. So limit comparison, if we do the test right, will work every single time. So for me, on the quiz you have next class, I'm going to make you use every test once. So this is a test I would look for first to make sure I can find one that does work. All right, let's try one more and we'll kind of go back to that what if that Nazi's asking because it's a really good one. All right. Tell your neighbor, what are we comparing to? All right, what would you guys compare it to? Ooh, I like that idea of simplifying that. So we're dropping the -1. Also notice my series starts at n equals 2. Again, that's because the first term, if I used n equals 1, would be undefined. What type of series is this? There's a P series. What's P? Why do I care? So what does this do? See, you walked in. Yeah. Yeah. So good notice. Kind of geometric kind of has a number to an n power, where this has an n to a number power. Good comparison there. All right, so let's look at, this is the one I want to know about. This is the one I do know about. Now, this question is a little different than the last two we did, because the one that I do know about diverges. So to make a conclusion, what do I want to happen? We want it to be bigger than a divergent series. Is it? All right. If you can see it from that inequality, I do think it will be bigger because I made the denominator smaller. If you want to convince yourself, again, we can multiply each denominator to the other side, subtract those square root of n's, and 0 is indeed greater than -1. So what could I say here? So just to go back, because Nazi was asking really good questions before, I want to re-explain. If I had instead had +1 here, would I be able to make a conclusion? No. So again, as you're rolling forward on the quiz we're taking next class, I'm going to force you to use each test one time. So for me, usually the first test I look for is nth term, because usually there's only one that works for that. Usually most of our terms are going to be going to 0. But this is usually the second test I look for, because it only works sometimes. Most of the ones we see for direct comparison are going to be ones that are a very similar series to something that's very simple. So notice I haven't been doing anything crazy here. I've been like subtracting 1, adding 2, adding 1. So these are going to be very close to our series, because we have to be convinced that this inequality is true. And if I change too much up, I get a little confused. So for example, the first one I'm doing here, do you think you could confidently write an inequality with greater than or less than to a simple enough series to compare it to? Probably not. So when we get back from our break, we're going to do limit comparison. We're only going to do 2. I promise you, you're going to like this test a lot. It works for a lot of things, kind of opens up the doors for things that are rational. So we're going to do that one, just 2 examples, and hopefully we'll at least start a notes check before we leave. Let's take 4, and I will see you back in 4. How about we take 2? I'm better at bargaining. What? Yes, it's gonna. I have a quiz review for you guys today. So there's 6 convergence divergence tests, and then there's some multiple choice. So like for this first one, notice P series, P series, P series. You just have to tell me which ones converge. This is a little bit of like geometric with some stuff, geometric with some stuff, P series with some stuff, some sums, and then there's like 6 of the big tests.
I think it's like multiple choice and then like notes check that we just did.
Yes.
Once I've memorized everything, I would really like this.
Yeah, that's the really important part, is like you have to know the conclusions. Practice makes it better. Yeah, if you don't know the conclusions, you're not going to have a good
I
time.
get like a different version of the notes check to like review.
Yeah, absolutely. Do you know which one you had? There you go.
Thank you.
Yes, ma'am. Okay. Sam.
Theoretically,
Theoretically.
if n was -2, would this work or not?
Well, if n was -2, these would both be undefined. So that's why it's nice that we started 2.
Okay.
Yeah, so you could actually, I forgot to do that.
Because like, if it's a bigger
Yeah.
negative direction,
So I'm going to run back to that in a second. So one thing I like to do because of that, you can, for this, you could write like 4n is greater than or equal to 2 here to emphasize that you're only doing that on the domain of this series. That's probably a better option. I forgot to add them here because I wasn't looking at my notes. But yes, I actually would add that. It'd be a good addition to our proof.
What notes are we doing? 8.5?
We are just reviewing and taking the quiz.
Okay.
Hello. Yeah, that would work.
And then this one I did, nothing like cancel out, so just diverge.
I would just keep going.
Okay.
It will cancel out
Oh,
eventually.
okay.
That one, pi/2, that is greater than 1. Yeah, that works. Feels like it's later than Wednesday. Ooh. I would change that plus to a times. I think you're doing it right afterwards, but I would change that to a times right now. I think that's good. That definitely looks
And this one
good.
didn't
Yep.
finish yet.
Yep, those look good so far. That one you might have to write out more terms just because it's hard to convince yourself which ones cancel.
Yeah.
But you can just keep going. You have the right test. Nate. Yeah, do I? We need to do my favorite number talks. Oh, it's going to bring me back to 2020.
Yeah. That'd be kind of.
I don't know.
3 seconds left.
What good timing. Mine? Wow. Exposed. All right. So I wanted to talk before we do limit comparison tests. Sam asked a really good question and kind of made me remember that I kind of forgot a little piece of notation, or at least like a little thing that makes this true all the time. So here's asking, like, what if the n was a different number and the inequality wasn't true? So for the square root one, it's not that important, but like technically for this first one, if n were like -2 or something, I could make this not true. So to be really rigorous in my proof, I should probably be notating like what domain I'm working on. So it would be nice if I could see like for n is greater than or equal to 1 after this. For n is greater than or equal to 1. So kind of just denoting that we're saying this inequality is true for the domain that we're working in. Yeah. There shouldn't be. So usually we'll create a series unless I make a typo. The series should be created so that all the terms are defined. All right, so let's go back and let's talk about this limit comparison test. So this test is going to start exactly the same way. We're going to be trying to find a thing to compare to. We're going to find that the same way by looking at the kind of biggest power, top and bottom, disregarding everyone else. Then what we're going to do is we're going to take a limit as n approaches infinity. Not surprising. That's what we've been doing for all of our limits for the last 8,000 years. And we're going to divide our two series. Now, we're going to expect to get a certain answer, and that answer is going to be a number that is finite and positive. Now, those words have a lot of meanings, but there's kind of some very specific meanings to these two. What does the word finite mean to you? Not infinity. Okay, so we should be getting a number. Now, positive is kind of a weird way to phrase this because we're already guaranteed that our terms are positive here. So it's not like we're going to get a negative number. What positive should really mean to you is that we're not getting 0. Now, if you're doing this test right, you should be getting something that is infinity, is not infinity, and is non-zero. So you should be getting something finite and positive. The what if of like, what if I do get infinity? What if I do get 0? That means you did something wrong. That means you chose the wrong thing to compare it to. Don't worry, that happens basically never. But that's kind of user error there. Now, the conclusion here, kind of like integral test, is the two series do the same thing. So if I get a number that is finite and positive, that means, hey, my test works. Then whatever I compared it to, the thing I want is doing the same thing. So let's try this twice, and then we'll see if we can hit that last notes check really quick. So compare to. Anyone got a prediction what I'm going to compare this to? What? All right. Logic. Let's go biggest power, top and bottom. So think back to like when we first started limits, like who's driving the top, who's driving the bottom. So we have n to the fourth over n to the fifth. I would argue this can simplify. Yes? Because this guy, think we're pushing n towards infinity. So this is getting really big, really fast. And the thing that's going to make this the biggest is that n to the fifth. So we want to choose the biggest thing on the top, the biggest thing on the bottom, and simplify. All right. If I simplify, I'm getting 1 over a singular n. What is his name? Harmonic, technically a p series. If you wanted to call it a p series with p equals 1, that's fine. More importantly, what does it do? Diverges. Now, like we said before break, I am not super convinced I could set up an inequality that would be any way convincing to my brain. So what I'm going to do instead is I'm going to take a limit of the ratio of these two series. I'm going to divide them. Now, I'm going to write this first step probably only in this question, and then I'll show you what I normally write. So here I'm going to take the limit of this giant fraction. So if you don't even want to write this guy, that's totally fine. Yeah. Canceled 4 n's from top and bottom. All right, then I'm going to divide it by this guy. So I'm taking the thing I want to know about and dividing it by the thing I do know about. Actually, the order of the division doesn't matter. But so I'm basically never going to write that because that looks gross. I hate it. What's better than dividing by a fraction? Yeah, multiplying by the reciprocal. So usually I will start right here. N to the fourth plus 5. That's a terrible division bar. Times n over 1. No, not necessarily. I like it just to remember that there's two fractions. All right, I'm going to, you might be able to see the answer to this question already. I'm going to distribute that n in the top to make it n to the fifth plus 5n all over that original denominator. Now, we have done a lot of limits like this, where n approaches infinity, and I've got polynomial stuff in the numerator and denominator. Anyone bold enough to tell me where this limit is going to approach? Yes. 1 over 3. We've got same power top and bottom. So we've made it to our ratio. We have 1/3. All right, now that we've produced a number, everyone's favorite question, why do I care? There, those are the words I want. Is this number finite? Yeah, it's not infinity. Is this number positive? Yes. So let's talk about what that means. That means that my test worked. Does that mean my series converges? No, because the thing I was comparing it to diverged. So we know that that means the test worked. So this guy, my question, my series, diverges by limit comparison test or LCT. Yes, LCT, good for both my test and the AP test. Yes.
So for this one, do you just go by like whatever you compare it to? So
Yes. So it's just like integral test where it's going to do the same thing as whatever you're comparing it to. All right, one last one before we leave. This is a good example of one that would not work for direct comparison tests. So let's say, what would we compare this to? 1 over n cubed? That's been our favorite one to compare to all day. Who is he?
Oh,
P series. P is 3, which is greater than 1. So this does what? Geometric and P series. All right, so here, if we wanted to use direct comparison test, remember we'd want this one that we're looking at, the n cubed minus 5, we'd want this fraction to be smaller than this guy if we wanted to convert as well. Is this smaller than this? No, I made the denominator smaller, so this fraction is bigger. So if I notice I have a direct comparison test that's not going to work, I'm going to roll right into limit comparison test. They both work for relatively the same kind of series. So I'm going to take the one that I want to know about and multiply it by the reciprocal of the one that I do know about. Now I can simplify this, but I'm betting everyone already knows where this is going. Hopefully. Rashad claims 1. You guys agree?
yeah.
All right. Still looking at the ratio of my coefficients since I have n cubed over n cubed. All right. Why do I care about the number 1? Finite. It's not infinity. Positive. It's not 0. All right. So what does that mean? That means my test worked. You don't necessarily have to write that, but what's my conclusion? Converges by LCT. All right. So I'm going to make a couple quick comments about the quiz and then hand out this notes check. Yes, ma'am.
Like the thing we did last time for like the 4 and is like
No, we don't have to here because that one was our inequality. We wanted it to be true on our domain. Here, we're dividing our nth terms, so we're good to go. So again, I'm going to pass out 2 things to you. One's going to be the notes check, and one is going to be this quiz review. If you were kind of on break and not listening to a couple of the questions about the quiz, this review for the quiz looks almost identical to the quiz that I have. So the back page is going to be your main focus. You're going to have 6 convergence divergence tests, and I'm going to require that you use the 6 tests that we know. I'm excluding P series because that tends to be a multiple choice question. So here, think about which tests you don't like very much. Think about which tests you're going to want to look for first. For me, the first test I always look for is nth term because there's usually only one where the limit doesn't go towards 0. Does anyone already see where the nth term question might be? Yeah, right there. 2 over 1. That's not 0. So I'd look for that one first. Then other tests that I don't like very much, direct comparison, because it only works some of the time. I'd be looking for ones that kind of look like another series that we've done. So maybe, I don't know, which ones do you think for direct comparison? Maybe one of these 2 on the left, because I can see turning that into a geometric or that into a P series, and I might be able to make that inequality work. So I'd do some front end kind of investigation. What do you think the bottom right one is? Yeah, he's kind of in your face. What do you think the 8 over 5 to the n is? Yeah, so what do you think this one is? Integral. Doesn't that one look like USEB? One on the top right. Yeah, the second one. All right, integral tests, technically, they could be anything, but usually integral tests, we're only going to pull out for complicated series. Ways to make it look complicated, make it look like USEB. So think about practicing those choices. And honestly, the most successful people I've seen take a quiz like this, do that front end work and try to pick out their series test before they even start going. So they go and they take all 6. They're like, all right, I'm going to assign my tests and make sure I know which ones I'm doing, and then I'm going to start. So that front end work is pretty helpful. If you need help choosing with those, I think I actually have some extra problems here underneath for choosing a method that we didn't get to today. Your problem set is also a great place to go for trying to choose a method. And then these questions on the front, these are more so focused on like all these first ones, which ones converge. Those are all P series. So you can just do your P series tests. And then other ones are more so about geometric or P series, kind of those simple tests at the front. Remind me, what are the 2 series where you know the sum?
Geometric telescoping.
Geometric telescoping. So it's going to be really straightforward. This quiz review, again, formatted identical to the quiz. So if you're feeling good about the review, you should feel good about the quiz. Answer key already posted. All right. So I'm going to come around with 2 pieces of paper, ma'am.
How long are we gonna have them for?
I'm thinking about a 45 break. So we'll spend the first half of class. You can work on the review, your problem set, whatever you want, ask questions. And then for about the last 40 to 45 minutes, we'll take the quiz so no one's feeling rushed. Also, it is, to be very clear, I know on the front of the problem set, it says a partner quiz. We used our partners for the last test. So that's going to be an individual quiz. Those tests are graded, by the way. And in your folders. All right. Notes check before you leave. Please read the directions. I told you which one to use direct and which one to use limit on. Don't ignore my directions, or I will ignore grading your question correctly.
So this has the art or is that limit? This whole year.
Bunch of good ones.
So it should be a really close adjustment
Detail.
on the
Oh my God. Gabby's just the better
All
spot.
right, you have 10 minutes to do 2 questions.
Oh, this is
I
gonna
believe in you. All right, coming around a second time with quiz reviews. If you don't want it, trash it.
Yeah.
Sorry. All right, I am taking these notes right before you leave, so I will get rolling.
I was gonna- Got it.
What? Oh, I don't know what to do.
Yeah.
I don't get a good for a 98.
Oh, wait.
This is so passive aggressive. You get a 99, you're on the way.
Yeah, if you scroll down, it's also.
I get that.
Only if you get 101.
I see convergence.
Alright, you're right. You're right.
Okay.
Don't say that.
1 over m squared, so we can use p series.
What about Ada? There she is.
There.
1 over M squared.
Yeah, it says.
Yeah, it tells you which one to use. I have a meeting. Everyone. Everyone say bye.